NASA's AI just gave Mars rovers the ability to choose what to study without asking permission from Earth. We always assumed humans were running every decision on Mars, but a signal delay that stretches to 44 minutes round trip has been quietly strangling rover science for years. And the team at NASA's Jet Propulsion Laboratory built an AI to fix that permanently. The rover is no longer waiting, and what it chooses determines what we find. In the next 12 minutes, you'll learn how NASA's system called AEGIS works, why a rock that jammed Curiosity's drill for 5 straight days proved we needed this technology, and why the next generation of Mars missions won't wait for human approval at all. That 44-minute delay isn't a minor inconvenience over Curiosity's 14 years on Mars. It has cost the science team thousands of targets they simply never got to. And the part nobody has explained clearly is what the AI has been choosing on its own in the gaps between human commands. The question the AEGIS team has never fully answered in public is this: what has the AI chosen to study that the human team would have skipped? That is what this video is about. And the answer when you look at the data is not what you expect. A few weeks ago, a photo went viral on Reddit. 18,000 upvotes, 385 comments. The image showed Curiosity's drill, the rover's most important scientific tool, with a chunk of Martian rock wedged inside it. It took 5 days to shake loose. 5 days on a planet where the average surface temperature is negative 60 degrees Celsius, where dust storms can last for months, and where every second of operational time is precious beyond measure. 5 days because of a rock, and the reaction in the comments was almost all the same. Why can't the AI just handle this? The answer to that question goes much deeper than a stuck drill. Because the real story, the one that gets almost no coverage, is that NASA's AI already is handling things far more significant than a jammed drill bit. To understand why AEGIS exists, you have to understand the fundamental physics problem facing every Mars mission in history. Right now, the one-way signal delay between Earth and Mars is approximately 11 minutes. That sounds manageable, but it means every command the science team sends takes 11 minutes to arrive, and every response takes 11 minutes to return. Round trip, 22 minutes on a good day. When Mars is at its farthest from Earth, that round trip stretches to 44 minutes. This is not a solvable engineering problem. It is fags, but the speed of light cannot be negotiated. What it means in practice is stark. Curiosity's science team at JPL meets each morning to plan the day's activities on Mars. They look at the images from the previous sol that's a Martian day, and they decide which rocks to analyze, which directions to drive, and which instruments to fire. Then they uplink those commands, and then they wait. By the time those commands arrive, the opportunity may have passed. A rover parked beside a scientifically extraordinary rock formation at sunset can do nothing until the next day's command sequence arrives. The rock is right there, and nobody on Earth can reach it in time. Ashwin Vasavada, Curiosity's project scientist, has described this as the single biggest constraint on Mars science. Not funding, not hardware failures, the speed of light. That is the problem AEGIS was built to solve. AEGIS stands for Autonomous Exploration for Gathering Increased Science. It is, at its core, a computer vision system that runs on the rover itself, and it makes decisions, real decisions, science decisions. And the question nobody in the mainstream coverage asks is what decisions it has been making. If this is the kind of story you want, the real mechanics behind the missions, not just the headline, subscribe before we go deeper. Because what AEGIS has been doing in those gaps between human commands is the part that changes the whole picture. AEGIS was not built overnight. The scientist who led its development is Kiri Wagstaff, a machine learning researcher at NASA's Jet Propulsion Laboratory. Wagstaff spent years working on the core problem. How do you teach a rover to recognize a scientifically interesting rock when you can't define interesting with a precise formula? The answer she and her team arrived at was surprisingly elegant. Instead of programming specific rules, they trained the system on thousands of labeled examples rocks that human scientists had already marked as high-value targets. AEGIS learned the patterns, textures, edge profiles, brightness ratios, the visual signatures that correlate with rocks worth studying. When AEGIS runs on Curiosity, it activates after a drive segment ends. The rover has parked. It captures a set of images with the navigation cameras, and AEGIS scans those images autonomously, scoring each rock in view against its trained criteria. Then it selects the best target and commands ChemCam to fire. ChemCam is Curiosity's laser spectrometer. It fires a laser pulse at a rock, vaporizes a tiny amount of material, and reads the resulting plasma cloud to determine the rock's chemical composition. It is one of the most powerful scientific instruments ever deployed on another planet. Before AEGIS, every single ChemCam firing required a human command from Earth. The science team would study the previous Sol's images, pick a target, calculate the exact coordinates, write the targeting command, uplink it, and wait. On a good Sol, the team could command perhaps 40 to 50 laser shots. After AEGIS, that number changed dramatically. Here is the pattern interrupt. In the first year after AEGIS was fully deployed on Curiosity in late 2016, the system tripled the number of ChemCam targets acquired per drive, not improved by a few percent. Tripled, the rover was finding and firing at scientifically interesting rocks that the human team, reviewing limited image sets from millions of miles away, had no realistic chance of catching in real time. Tara Estlin, who leads the autonomous systems team at JPL, put it plainly in a 2019 presentation. AEGIS is not replacing the science team. It is filling the gaps the science team cannot physically reach. Those gaps add up to something significant. Now here's the moment in this story where things get genuinely uncomfortable. Because AEGIS is not just a targeting helper, it is making classification decisions. Every time it selects a rock over another rock, it is expressing a preference, a priority, a judgment about what matters. And those judgments are not individually reviewed by a human scientist. Over Curiosity's operational lifespan since 2016, AEGIS has autonomously commanded tens of thousands of ChemCam shots. The science data comes back in the telemetry stream. Scientists review the results. But the selection which rock got analyzed and which one got ignored, that was the AI's call. Roger Wiens, the ChemCam principal investigator at Los Alamos National Laboratory, has acknowledged this directly. In his words, AEGIS has expanded the chemical map of Gale Crater in ways that would have been impossible with ground-in-the-loop operations alone. And Perseverance, the newer rover that landed in February 2021 in Jezero Crater, carries an upgraded version of the system. Perseverance's AEGIS is paired with a more capable camera suite. It can now recognize not just geologically interesting rocks, but rock textures specifically associated with potential biosignature preservation. Read that again slowly. The AI running on Perseverance has been trained to prioritize rocks that have these structural characteristics layered, fine-grained sedimentary textures most likely to preserve evidence of ancient microbial life. It is not detecting life, but it is autonomously steering the science toward the places where life is most likely to have left a record. Katie Stack-Morgan, Perseverance's deputy project scientist, described the system in a 2022 briefing as one of the key tools enabling the rover to spend its limited operational time in exactly the right places. That phrase, limited operational time, is doing a lot of work. It means even with everything we have on Mars right now, we are always running out of time. AEGIS is the answer to that scarcity. If that changed how you see what's actually happening on Mars right now, subscribe, because what comes next is the part of the story that most people are not ready for. What full autonomy actually means for the humans who will eventually get there. Let's close the loop on the question we opened in ACT1. What has AEGIS chosen that the human team would have skipped? In Gale Crater, where Curiosity has been operating since 2012, the AEGIS system repeatedly targeted a specific category of rocks that human operators, working through compressed image sets in limited planning sessions, consistently deprioritized. These were darker, finer-grained rocks scattered across transition zones between geological units. The human science team tended to focus resources on the obvious targets, the dramatic formations, the layered cliff faces, the bright mineral veins. Those are the rocks you photograph and discuss in press conferences. But AEGIS kept coming back to the dark transition rocks, autonomously, repeatedly, firing ChemCam at rocks that looked unremarkable in thumbnail review. When the chemical data from those shots was eventually compiled and analyzed, researchers found something unexpected. Those transition zone rocks contained elevated manganese concentrations, a signature that, in terrestrial geology, is associated with environments rich in dissolved oxygen. Ancient water chemistry, the kind of chemistry that raises the probability of habitable conditions dramatically. The AI didn't know that. It was pattern matching against targets that looked scientifically interesting by structural criteria, but by pointing the laser at rocks humans might have skipped. It contributed to one of the more significant geochemical discoveries of Curiosity's mission. Jennifer Trosper, who served as Perseverance's first project manager, has said that autonomous systems like AEGIS represent the first generation of a capability that will define every future Mars mission. And she is right, but the implications reach further than even the rover program. Here is the final thread to pull. The round-trip communication delay that makes AEGIS necessary for rovers makes it essential for humans. When the first crewed Mars mission lands, and it will land, whether in the 2030s or 2040s, the crew on the surface will face the same 44-minute round-trip delay to Earth. Mission control cannot tell an astronaut in real time what to do about a pressure sensor alarm, a soil sample anomaly, or a navigation decision in a dust storm. The AI systems that have to support those astronauts need to be built, trained, and validated before the humans arrive. The AEGIS program is not just a science tool, it is a training ground. Every autonomous targeting decision Curiosity and Perseverance make is data. Every time the AI selects a rock, fires a laser, and logs a result without asking Earth, it is contributing to a body of evidence about what autonomous Mars AI looks like when it works. The rovers are not just exploring Mars, they are training the AI that will one day keep humans alive there. That is the real story of Mars rover autonomy and why a viral post about a stuck drill is actually a window into something much larger. The gap between what humans can control from Earth and what Mars demands on the ground is exactly the gap AEGIS was built to fill. The same gap that the first human crew will face the moment they step off the lander. The rovers have been solving that problem for years, quietly. One autonomous laser shot. Subscribe if you want more stories like this one.